For this lesson, we're going to look at distinguishing between rational and irrational numbers. So for the first one, if we plug 28 over 11 into our calculator to turn it into a decimal, we find that we get 2.5454554, and we know that it's just going to keep repeating on and on forever. So if this is true, then the decimal that represents 28 over 11 has a repeating pattern, and it does not terminate. It's going on and on forever, like I said. If I take 28 over 8, then 28 over 8 is the same as 3.5. 3.5 doesn't have any repeating pattern, but it terminates. It's got an endpoint where after the 10th digit, there's nothing afterwards. If I took the square root of 2, the square root of 2 is the same as 1.414213, yada yada yada. In this case, there is no repeating pattern we can see, but it just keeps going on and on forever. So when we talk about repeating decimals, they're just decimals that have a repeating pattern. The pattern could be one digit where it's like 1.33333333. It could be two digits where it's 545454. It could be three digits, four digits, five digits, however many, where once we get to the end of it, it just keeps looping that pattern over and over again. Non-repeating ones are ones like pi, where they have no repeating pattern. We can't find a pattern that ever exists. Terminating decimals are ones that have a finite number of digits, where they have an endpoint like that 3.5. And non-terminating ones are ones that are going to go on forever. So we can double check this by looking at these or plugging them into our calculator to find if they're repeating or non-repeating and whether it's terminating or non-terminating. When I plug 1 over 8 into my calculator, it doesn't have a repeating pattern, but it does end. If I put 2 over 11 in my calculator, it does have a repeating pattern, but it does not end. Nine over 7 also has a repeating pattern and does not end. We can see that from the decimal 0.94 with a line over the 4, that line over the 4 means that the 4 keeps going on and on forever. So this is repeating and non-terminating. When I get to the square root of 8, there is no repeating pattern, but it seems to go on forever. And when I put the square root of 0.16 in my calculator, I just get 0.4. So this one is non-repeating, but it does terminate. The significant one here is the square root of 8. It's the only case that we had where it doesn't repeat and it doesn't terminate. Well, when I'm distinguishing between rational and irrational numbers, a rational number literally means it can be written as a ratio of two integers. In order for it to be able to be written as a ratio, it either needs to terminate or it needs to have a repeating pattern. So as long as it has a repeating pattern, you can turn it into a fraction. If it has an endpoint, you can turn it into a fraction. The irrational ones are ones that are both non-repeating and non-terminating. Those are ones like the square root of 8, I can't really represent as a decimal or as a fraction, because if I do it as a decimal, I'm going to have to round it at some point. If I try and put it as a fraction, it's impossible. It doesn't work. So, as long as it is non-repeating and non-terminating, it is going to be irrational. So we can see that with example A, if I have 1.493, it's got an endpoint here. So this is rational. When I put the square root of 5 into my calculator, then it goes on and on forever without a pattern. This is irrational. Non-repeating, non-terminating. When I get to C, I can see it's got this repeating pattern of 3, 4, 7, which means that this is rational. When I plug the negative square root of 81 in my calculator, I just get negative 9, which terminates, so this is rational. When I put the square root of 4.41 into my calculator, I get 2.1, it terminates, this is rational. When I get to F, it certainly looks like there's a pattern here, but it's not a repeating pattern. Here I have 2 1s and 2 2s, then I have 3 1s and 3 2s, then theoretically 4 1s and 4 2s. I need to have the exact same number of the exact same digits for it to be considered repeating, which means that this is actually irrational. I can always represent any of these numbers on a number line, giving an approximation of what their values are in relation to the digits on the number line and to each other. The easiest way to do this is just plug the numbers into my calculator to see approximately what it is that I'm getting. Well, if I put the square root of 14 into my calculator, I get 3.741 and then just a non-repeating pattern. If I take pi, most of us already know it. Pi is 3.14, and then it's just going to keep going. If I take the square root of 80, that's going to be 8.94, and goes on and on forever. If I plug 2 times the square root of 15 in my calculator, I get 7.74. And the square root of 0.1 is going to be 0.316. I can take these and draw them on the number line, where I can see that square root of 14 is approximately 3.74, so it's going to be in between 3 and 4, and it's going to be closer to 4. And I can say that that is A. I can say that for B, pi is 3.14, so it's going to be closer to 3, and there's approximately where my B is going to go. The square root of 80 is going to be just shy of 9, and that's where C would exist. 2 times the square root of 15 is 7.74, so it's going to be about there. and e is just above 0. So I can always just find approximately what they are to 2 or 3 decimal places, and I could arrange them accordingly or stick them on where they would fit on a number line. Now, I can use my graphing calculator to do this. I'm going to put in 0 point, and if it's got a repeating pattern, like this would be 3.9555, and then just keep writing fives over and over again, and I can use that math frac button. Some of you have a fraction to decimal button, whatever it happens to be on your calculator. This one I can see is 4/11, and this one would be the same as 178/45. Now, when I'm converting from a repeating decimal to a fraction algebraically, you're not required to do this for this course. So, if you want, you can look through the process. I would take the original number represented as x, I'm going to move the decimal place over, and then I'm going to write it as a fraction. If I have this, where 1,000 x's is this, 10 x's is this, and I subtract them from each other, then what's going to happen is (1,000 x's minus 10 x's is going to leave me with 990 x's. And that's going to equal to everything after the decimal. That 5-1 going on forever is going to cancel each other out. And I'm just going to be left with 2,031, which means that x would equal 2,031 over 990. And theoretically, from here I could double check and say, can I reduce this fraction? Well, the top number and the bottom number are both divisible by 3, so it's just going to be 677 over 330. Remembering that you don't have to do it this way, you can use your calculator. Go ahead and get some practice.